Hello, everyone. We're continuing our discussion on data mining algorithms uh, under the context of optimization and on that underlying algorithms. So let's continue our discussion with decision trees and random forest. Decision tree algorithm is widely used algorithm for classification, which uses attribute values to partition the decision space into smaller subspace iteratively. So just to be aware, it's a divide and conquer approach, and then starting with the root node, gradually grow to a final classification, which would be a leaf. We consider to be a leaf. And then the decision process can be represented graphically as a tree, even though more like it's a tree, inverse tree, which is from the computer science perspective, we have this concept to call it as a tree, meaning it's an inverse tree. And then these trees are directed trees, but they're unique. They're not unique depending on which attribute to use first. So let's use this specific example to be a hypothetical classification system for a university degree. Suppose that a student has to take different modules and major dissertation or thesis for a degree, and each module subject has an exam. The minimum pass marks are 40%, and then for each thesis, 3 grades, merit, pass, or fail are given. A Bayes system is used for the hypothetical degree program, as shown in the next slide, to see that for different mark, what's a chance that what would be output in terms of merit, pass, or fail. If a student gets all the modules with a mark above 80% with a merit of his or her thesis, a first-class degree will be awarded to the student. And then the final classes are first class, second class, or third class, or pass. So you can think of this as there are 2 dimensions. One is how much mark he got for the class, and then second dimension is what is the grade for the thesis. And then based on those 2 dimensions, a final grade will be assigned. The final grade will be first class, second class, third class, or pass. Now this is an example. So from x-axis is module exams, marks for the module exams. The y-axis would be thesis marks. In here you can see that for thesis marks there is no fail. It's either pass or merit. A good one, or it's a pass, or it's an excellent one has a merit. So now if you think about this classification, essentially says, if for the module exams, the student get more than 80%, and the final exam thesis marks turns out to be merit, then this type of student will get a class 1 grade. And then if module exams, he got more than 80, but he only got a pass for the thesis marks, then he can only get a second class final grade. So this is a decision tree essentially. Let's take a look at one more. Right, if the student get 40 to 60 as a module exam mark, and as a thesis he only got a pass, then overall he can only get a pass for the final grade. This can be represented by a decision tree. So the first decision variable is whether the student get a pass or merit. If he get a pass, then let's check his exam score. If his exam score is larger than or equal to 80%, then he should be belonging here, which is second class of the final grade. If he didn't get a larger than or equal to 80, let's check what would the behavior gain get. He is getting larger than or equal to 60. Yes, then that would be third class. If it's less than 60, then it's a pass. Basically, this side of the tree essentially representing what's happening here on the graph. Same thing happens on the right-hand side. You should take a look, then you know this is what decision tree is. Of course, question 9 becomes, why did we start with pass or merit? Why can we start with module exams? Yes, that would be the question that decision tree is trying to answer with different algorithms. Let's take a look at the ID3 algorithm. ID3 is a popular algorithm in decision tree. It's called iterative dichotomizer 3. Uses an information gain as a rule to select the attribute that can explain the training examples and maximize the information gain. So let's take a look at, remember that we define this quantity called entropy. Entropy is the discrete value probability P1 times log 2 P1 with a minus sign plus the second probability with a minus sign. So that's our entropy definition. And then in case of multiple k-classes, we can do the same. Summation of every pi times log 2 pi, I from 1 to k with a minus sign. And then pi is a fraction or probability of sample belonging to class I. So another related concept is Gini index or Gini impurity, which is negative of the entropy. It's called GI. So if you ever come across some packages that come back with specific metrics such as Gini index, now you know that Gini index is negative of entropy. Now, what is information gain? The information gain is of a specific attribute A with possible category values of xj. J belongs to 1 to k other categories, is defined as using this entropy that we defined in the previous slide minus fj times xj. Xj belongs to class A. So let's take a look at all the definition here. Omega A is a set of categorical values of attribute A. Let's say attribute A is the thesis marks, pass or fail or merit. Then it would have 3 different values. That would be the omega A, pass, fail, or merit. And then Fg is a fraction of value xj belong to A. See that what's a fraction of students actually getting a merit. That would be your Fj, which can be calculated by the ratio of the number in Axj of xj to the total number of values, or cardinality. In other words, how many students in the class. And then the Sxj is the entropy, which with a similar formula to the entropy S, though its fractions are based on the categorical values of that particular attribute. Now, so what we do here is, for ID3 algorithm, once we have this S and information gain, what you do is load the data and calculate the same sample entropy S first. And then for attributes, for all the variables, find the attribute with the maximum information gain, IGA, and then split the set into subset by values of the best attribute. The best attribute is the attribute that has a maximum information gain. And then create a decision tree node for that attribute with IGA max. Iterate over the rest of the unused unsplit attribute, and then construct a decision tree. The ID3 is simple and can work well. However, it is a greedy method and there is no guarantee of optimality. In addition, it can handle continuous dataset. That is ID3 algorithm. It's just how to decide which variable comes first. Of course, all of this is already implemented in the packages. When we leverage those packages, we just use those specific terms, but at least for now, you need to understand this theory so that we are able to understand the output of those algorithms. Now let's take a look at the example that we have for the hypothetical degree classification example. So let's look at how would the ID3 work on that example. First of all, we final mark that student can get would be four categories: 1, 2, 3, and pass. And then we know that there are 12, 9, 6, and 3 who get those marks respectively, so that we can get P1, P2, P3, and P4. And based on those probability, you can calculate the entropy of this example. So it turns out the entropy to be 1.8464. Now I'll give you some specific numbers for the first attribute, that is thesis marks. So assume that there are 20 of the students students are merit to get a merit score for the thesis. 10 of them are just pass. The rest of them 0 would be fail. And then for merit, their corresponding student classes are this many for 1, 2, 3, and pass. So 16 for 1, 2 for 2, 1 for 3, and 1 for pass. And then for the thesis with pass, they have 2, 2, 4, 1 for the 1, 2, 3, and pass respectively. So the attribute thesis have two values, either merit and pass. For all the 30 students who got a degree. So the fraction for merit and pass are 20 over 30 and 10 over 30 respectively. So that would be our Fi that we have in the previous slide. And then F1 is 2 over 3 and F2 is 1 over 3. And then for each one of them, 2 over 3 fraction for the merit, the corresponding fraction is 16 divided by 20, etc., with corresponding probability, so that we are able to calculate this entropy based on this specific attribute, which is the thesis marks, and it turns out to be 1.0219. Then we can calculate it. Similarly, we can calculate the entropy for the second variable, as x2 turns out to be 1.92919, and then we use those two together. We calculate the information gain for thesis to be 0.5245. Therefore, the information gain by using thesis marks as a decision criteria is 0.5245. Now, the question is, if we use the instead of thesis marks, we just use module exam marks, what would be the information gain. And then based on those two, we can compare and make a decision on which one we should be choosing. So here we just use an example to tell you how you can calculate information gain. Of course, all of this are already implemented in the algorithm ID3. As an exercise, you can use R or Python to implement this example to come back with a corresponding calculation. Let's take a look at a different algorithm. It's called C4.5. So we know that ID3 cannot deal with continuous variables, as we mentioned earlier. C4.5 can deal with continuous data and missing data. Pruning is used in C4.5 so as to reduce the depth of the trees and remove unnecessary or insignificant branches. Pruning is a concept that is commonly used in the tree context. So we'll discuss shortly on what is a pruning. So first thing is, let's define this that is called split information. Split information of attribute is an entropy of this function form, where fi is a fraction or probability of the data in category I among the whole data set, and information gain ratio is information gain divided by split information. So just be aware, right? The previous algorithm, IG3, will have information gain. Now we said, let's define a new variable that is information gain ratio, which essentially is the information gain normalized by the split information. Okay, and then C4.5 is based on information gain ratio. So let's think about what is a pruning. Pruning is to remove the subtree or child nodes of the decision node and turn the decision node into a leaf node by giving it with the most common classes among the training data. So hold on. So essentially saying that at a certain point, we have to stop. We cannot just continue to use all different variables to continue to split the tree. So here it says at a certain point you would stop. You remove the subtree or child node of the decision node and turn the decision node into a leaf node. Leaf node is essentially the bottom of the tree is just stop there, and giving it the most common class among the training data. That is pruning. So the main steps of the C4.5 are just like that, similar to IG3, except that it calculates the normalized information gain ratio rather than information gain, and then find the attribute with maximum IGR and go from there, keep continue and loop through. So for continuous variables, how does C4.5 is dealing with it is trying to convert the continuous variable into a Boolean attribute at certain critical value of x star. If a is larger than or equal to x star, then we give a value of 1 or true. Otherwise, we give a value of false or 0. And then x star can be any decision boundary that would be appropriate for that attribute and decision making. And just to, just be aware that both of those algorithms are already implemented in the app and Python packages, so you can leverage the packages directly. So just just a natural extension of decision tree. When for large data sets, you have a lot of have a lot of variables, independent variables, x1, x2, x3, x4, x5, etc., etc. Then you have to use multiple tree simultaneously, and use multiple random trees simultaneously lead to the random forest algorithm, which we're going to discuss next. So what is a random forest? You probably ever heard of it already, but now you know you understand decision tree. You just need to realize random forest is an extension of decision tree. So what it does is it constructs multiple decision trees randomly using sampling with replacement. And final decisions are based on a voting system of the tree ensemble. Tree ensemble essentially says all the candidate trees give me some sort of classification for a particular observation, but they give some sort of conflict output, right? Maybe among these 1,000 trees that I built, 900 of them says observation 1 belongs to class 1, but the rest of them says observation 1 belongs to class 2. Then you know if you use a voting mechanism, the output of your final model should be class 1 because it has more tree giving a class of class 1. So that's a voting system. So let's take a look at how do you construct this multiple decision trees. So essentially saying that you have 1,000 dimensions. Now we randomly pick 100, for example, or maybe less than that, 20 of them. And then using this 20 to build a decision tree to classify all the observations. And then you can build this tree multiple times. You take 20 random attributes and build for all the observations and build a decision tree and put those 20 variables back. Take another random sample of this original 1,000. That's what we call with replacement. And then build another decision tree. So you have multiple decision trees, a lot of the decision trees, and then use all of the decision trees to get your voting output. So that's why we call it random forest. It's built upon decision trees. Now question becomes, how can we come back with a proper number of features, or in this case, M. Initially, we have D features. In my example, I said 1,000, and then and also in my example, I said let's choose 20 of them. M is the feature for splitting the data at each decision point, and you could use M would be rounded to the nearest integer of square root of D, or M would be log 2D to determine the M. So now, and also among these M features, the training samples are randomly selected from the original data set with a replacement as well. Then each subset is fed into the decision tree classification, and classification is based on the majority vote of the ensemble. And each tree can cast a single vote for the most popular class for an input feature vector for one specific observation, so that at the end of the day, you would have a vote for each individual observations. In other words, you would have a classification for each of the observations. Now, this is algorithm. Start with the data initialized for a given number of trees. Do this. Select M features from the D features sample data to create T different trees, create each tree by iteratively splitting, forming decision nodes, and predict any test feature by running the multiple trees, classify using majority voting. So that's random forest. Now, give you an example. You have tree 1, tree 2, everything all the way to tree K, and then each one of them would have some sort of structure, right? And then you would have a classification for each individual observation, and from all the trees, then you take what happens the most based on the voting mechanism and make a decision on what would be the corresponding class for one specific observation. Computational efforts tend to be high due to multiple trees, typically a few thousands to a few hundred trees. So just be aware, random forest has a lot of computation involved. And usually it do not lead to overfitting just because of the random sampling and the sampling with replacement mechanism that put into place in that algorithm. But overfitting can still occur for noisy data. Just be aware, right? The third note that we want to point out for random forest is there are many different variants of random forest, such as the kernel random forest and boosting methods. As an example, ARA-boost is one of the boosting mechanism that can be used in random forest. Okay, we'll stop here for this section on decision trees and random forest. Thank you.